One of the biggest successes we've had with LIQUiD is simulating quantum chemistry. We spent a lot of time building a tailored simulation system so that we could do some interesting chemicals. We can't go much bigger than about 30 qubits on a classical machine, but that's enough to do some interesting chemical analysis. We can also build circuits for much bigger systems, for real quantum computers on the order of 1 to 200 qubits, but we can't run them. We can look at gate counts. We can look at how long they would take to run on the quantum computer, and that's what's important. So we started with an interesting problem, which is a chemical called ferredoxin, Fe2S2. This little chemical sits at the heart of photosynthesis. It's also in your bloodstream, in your hemoglobin, and is used as an energy transport to move other molecules around. Quantum chemists would like to analyze this chemical, but the problem is the molecule has ions in it, and ions have d orbitals, which are notoriously hard to simulate on a classical computer. So we looked at how hard this would be. When we first started, the accepted state-of-the-art for how they thought they would do this on a quantum computer, if you ran the numbers, came out to a circuit that would take 24 billion years to run on a quantum computer. Now that sounds terrible, but to run it on a classical computer would have been longer than the lifetime of the universe. So actually it's a big win, but it doesn't make it down to human time frame. Over the course of 2015, we wrote 4 papers doing research in this area, and each paper lowered the time it would take to actually run this on a quantum computer until the final paper we got down to 1 hour from 24 billion years. Pretty good speed up. And the papers are referenced on the website after this video if you'd like to see the papers themselves. I'm bringing this up because one of the interesting points here is how did the quantum simulator help us? The one thing LIQUiD did is it let us try some small chemicals and small molecules. And these small molecules, when we simulated them, simulated much, much faster to much higher accuracy than the theoretical results would have told us. Many, many orders of magnitude faster. So we were able to go back to the theorists and say, are you sure about the theory? And they said, oh no, you're not simulating everything. And I said, well, we're getting the right answer. Try this molecule. We tried that molecule. We went back and forth, and after a while the theorists realized that chemistry has some very specific things about it, which are documented in the papers, that we could actually do much smaller circuits and run them much fewer amounts of time to get the same accuracy. So this was a good example where a quantum simulator, even with only on the order of 30 qubits, was able to inform a result for future quantum computers that may be 10, 20 years away of how hard something would actually be to run and what you could really accomplish with a quantum computer. We're now looking into first level problems, things like better fertilizer algorithms, ways for making fertilizer with less energy, carbon capture to solve global warming. All of these fit in this quantum chemistry area, and we're doing a lot of work now to see what would you do with the earliest quantum computers that can actually run this size problem.